finishing up chapter 11, where they derive the result we're going to get through a lot more work. Again, you should go through it, you should look at it, but I think it's easier to see with what we've done. Let's define something. This is the Greek letter mu, right? We've seen it before. We've seen it in these formulas as a mu naught. Unfortunately, this is not the same mu. Again, I didn't do it. Don't send emails to me, right? That is the magnetic permeability. This is just a mu. I'm going to define this as, and this is a vector, right? As this. I, A, N hat. Alrighty then. What does this mean? I is a current, clearly. A is an area, and N hat is an N hat. Okay, so what does this mean? If I have a loop of current, like what I just drew and erased, this loop, just by virtue of being a closed line, has a cross-sectional area. And I'm not talking about the cross-sectional area of the wire. I'm talking about the area formed, or the area enclosed by the wire itself. So everything I'm shading. Right? That's the area formed here. I times A, the current magnitude, times the area, gives you this quantity here, which is called the magnetic moment of the wire. In effect, this is a shortcut to calculating the magnetic field here. It's not quite the magnetic field, but it's something very, very similar. N hat just means the same as it did earlier. It's a vector normal to this plane with the direction given by the right-hand rule that we just learned, right? Fingers in the direction of the current. Stick your finger up. There is your magnetic moment mu, which functions really, it is a magnetic field. If you want to calculate the actual value of the magnetic field here, go to the other formula. But this is basically how we talk about the magnetic fields of loops of current. Where am I going with this? It's a simple calculation, first of all. If you know what the radius is, the area that is just pi r squared, right? It doesn't have to be a circle, it could be a square. Different area formula, but the same idea. Okay, why am I doing this? Well, this is a magnetic field. Fields are going to interact with other fields. Okay, so let's look at it. Here is a background magnetic field coming from somewhere we know not where. Here is a loop of current, and as I've drawn it, you kind of have to know which is in front and which is in back, right? Again, it's a byproduct of two-dimensional drawing. If you ever have questions on exams, remember, just ask how it works. In this one, I'm thinking this is in front, this is in back, so it looks like my magnetic moment looks like this. If I do the right hand rule, wrap it around, stick out my thumb. Okay. So my magnetic moment here, mu, my background magnetic field, V, right? These are magnetic fields. In effect, this is now a magnet like you have a bar magnet or a magnet on your refrigerator. And it's just like when you bring that bar magnet next to another magnet, they experience forces. There will be an interaction here. This magnetic field is going to attempt to line up this magnetic moment with itself. So if this wire is free to rotate, it will do so. If you give it enough time, it will later come into a position that looks like this. The interaction between the fields produces motion. Now, how would you characterize this type of motion? What are we talking about here? A translation? What are we talking about? It's a rotation. Can you think of applications for rotating objects? This is how a motor works, an electric motor. This is exactly how an electric motor works. You're going to build one in the lab, I think next week. It's actually a really cool lab. This is exactly how an electric motor works, right? You run a current through a coil. That current through the coil produces a magnetic field that looks like this. Then if you let that interact in a background magnetic field, it lines up the vectors. So what happens is if you turn something on, right? Either you turn on the background field, or you turn on the current that produces this field. When you turn it on, if it's in this orientation, it will spin, it will rotate around to this position. Now, here's the kicker. It's not going to stop because this thing has mass, ergo it has inertia. So what happens? Well, if it starts out like this, it's going to rotate around to this position, but it keeps on going. Its inertia carries it through to the symmetrical position here. So it's speeding up. It's at a maximum speed. It slows down. It stops. But now the whole thing starts over. Speeds up, maximum speed, slows down, stops. So what you get is an oscillation, back and forth, back and forth, back and forth, back and forth. That's obviously not good for rotation, right? That isn't rotation. It's oscillation. So, what do we do with that? Well, you have some options, right? The way this is handled usually in DC motors is to turn off this current halfway through the cycle. So see, where does the rotation, the torque, it's a torque, where does the torque flip direction? It's right here, right? Right in this position, the torque is making this thing rotate here. But once I get past this point, the torque is acting oppositely, right? My angle has flipped, therefore the sign of my torque is flipped. So maybe a strategy would be to turn off the current here, which means that there is no magnetic moment now, right? This thing then by its own inertia continues to go to here. And then I turn the current back on. And then that gives it a kick to here, and I turn the current off. And it, under its own inertia, goes here. Turn the current on, kick it, off, on, off, on, off, on, and it rotates. Okay. They do that in DC motors by just breaking the circuit. It's called a commutator. It's basically a gap in a metal ring. I can't draw it. There's illustrations in your book if you're interested. You're going to build one, so that's cool. And how you handle it in lab is actually pretty ingenious. But basically, they have a metal ring that rotates, and there's a gap in it. It's not a complete gap, the metal ring comes down. And they have a brush that's in contact with that ring, and in the gap, it loses contact, and there's no current, right? So it picks up the current on the next half of the cycle, and so it gives it a kick, keeps it going. This is how DC motors work. AC motors work differently. We don't really talk about AC here, but if you know anything about AC, you know that the direction of the current goes back and forth. If you flip the current direction, you flip the magnetic moment, right? So every half cycle, this guy just changes direction, and you get continuous rotation. Okay? So this is how a motor works. There is a torque produced here. The torque, mu cross B. So torque in 1600 was R cross F. Now it's mu cross B. Not particularly easy to handle because mu is constantly changing in direction, or probably. But let's unpack this and see what we get. By definition of the cross product, we've got magnitude of mu, magnitude of B, sine theta. I'm going to leave off the vector nature. We're just worry about the scalar. Okay? Magnitude of the magnetic moment we've already seen is calculable as IA, B from here, sine theta. Okay. This tells you that if you're going to produce a torque, there are several different ways to do it. You can change the current, which is what the solution was here in the DC motor in the commutator. You can change the area of the loop. That's a little difficult, but there's situations in which you can do it. Railguns You can change the magnetic field. That's a possibility. Or you can change the angle between them. Any change in any of those is going to change your torque, right? So how you choose to formulate that is kind of up to you as an engineer and your design specification. But a change in any of those things will produce a changing torque. All right, questions about that? This leads to a couple of important relationships. This is one of them. I'll show you this. The torque on a loop of current is mu cross B. We also have this expression. Potential energy is going to be this. Minus mu dot B. Okay. This is an interesting one. In general, we tell you that you can define your 0 point for potential energy wherever you darn well please, but this is somewhat of an exception. So let's think about that. Here's a magnetic field. I'm not going to draw all of it, but I'm going to draw 3 situations. Imagine that this is a field that permeates the whole board, right? So here I have this magnetic moment in this position, magnetic moment in this position, magnetic moment in this position. So I've given you 3 different orientations of a current carrying loop in this magnetic field. All right. What is the potential energy of this magnetic moment in this magnetic field? You can see it from the cross product here, but you can also just think about it. If you turn the current on in this field, is this thing going to move? No. Right? So we would probably tend to say the potential energy here is 0. That's how we handle gravity, right? What's the potential energy of my keys right now? You'd probably say 0. Although you could say something non-zero. If I reference the ceiling, it's negative. If I reference the floor, it's positive, right? You can choose that. But probably we're going to reference the table and say 0. And that's because they're not going to do anything no matter how long I wait. If I pick them up, then they have the potential to fall, right? Right? So it would be following the same logic. We'd probably be tempted to say the potential energy is 0 here. And you can do that. It just turns out that the math isn't as pretty as you do that, right? Do we all agree that there is some potential energy here? Yeah. If I turn the current on, this thing's going to move. Here, would we agree that the potential energy here is maximized, right? It's minimized here. The thing's not going to move. It's maximized here. It's going to move all the way around. It's somewhere in between here. The way we handle this, and this is just a convention, so use it if you please. But in this class, you should use it. That's where I get this negative sign here, right? So what we do is we reference this as our 0 potential energy and say this has some positive potential energy and this has some negative potential energy. It actually comes out, this is why we have the negative sign here. This comes out as, what that does is it enables us to use this nice form here. Because buried inside this dot product is a cosine, right? And the cosine of 0 is 1. The cosine of 90 is 0, right? So choosing this point as our 0 point matches up this formula. We don't have to do this, but if we define our 0 point anywhere but here, we can't use this, and this is nice. Does that make some sense? So here we have 0, here it's negative, here it's positive. That'd be the same thing as asking myself, well, what are my keys' potential energy? Well, mg times minus 10 meters from the ceiling, right? You're just moving your 0 point around, but you're moving it around cleverly so you can use that formula. All right? So that's the torque of a magnetic moment in a magnetic magnetic field, that's the potential energy of a loop of current in a magnetic field. All characterizable using this new thing, the magnetic moment, which is just IA times the normal current. Questions about any of that? Okay. All right. Hang on to most of that, because that comes out to be important later. Basically, we've seen how an electric motor works. Okay. Any questions about any of that? All right. One more thing from chapter 11. It's the last thing. In the section in chapter 11 where they derive basically what we just got using the so assuming you go through the book in order, in chapter 11 you don't have biots of art yet, so we don't even know that fields arise from currents yet. So they do it different ways, which is totally fine. It's worth going through, but I think it's more fundamental and easier to see how the fields interact and worry about the forces exerted on the lines of current. But if you do that, an interesting result comes out of that. So we're skipping most of that stuff, or at least we're doing it the easy way. But there is one thing I want you to see. Let's take a line, let's take a square loop of current. So let the current run this way. And I'm going to encase this in a background magnetic field. Right. And this square is going to be side L, all sides. And let me remind you of a result we saw, I think, the last time or the time before that. The force on a loop of, or on a current carrying wire in a magnetic field is given by this. ILB sine theta. I shouldn't make that a big. This is just the result we got, or that I gave you, and we talked about it a few times ago. So let's ask ourselves about the force, the magnetic force on each of these sides of current. Okay? Up here at the top, we'll call this 1, we'll call this 2, we'll call this 3, we'll call this 4. Alright, ILB sine theta. Well, there's definitely an I haven't given it to you, but here it is. There's definitely an I, there's definitely an L, this has a length. There's definitely a V, I should label all my things. What about the sine of theta? What is theta between the current and the magnetic field on the top loop, or the top leg? Theta is 0, so what's the sine of 0? 0. So is there a magnetic force exerted on this leg? No. Same thing with the charged particle moving in the direction of the field. What about the bottom leg? What is theta between the current and the field here? 180 degrees or pi radians, however you want to think about it. What is the sine of either one of those? Sine of pi is 0. Sine of 0 is 0. Sine of pi is 0. Right? So what is the force down here? 0. Okay. Well, here, I've got an I, I've got an L, I've got a B. What is theta between the current and the field here? Pi over 2 or 90 degrees. What is the sine of 90 degrees? 1. So we've got a force here of ILB. What about this one? What's it going to be? So you said the angle between the current and the field here is 90 degrees. By your definition of what 90 degrees is, what is the angle here? 270. What is the sine of 270? Minus 1. So what is the force here? Minus ILB. What is the total force acting on this loop? What is ILB minus ILB plus 0 plus 0. Now, I'm going to go ahead and tell you, this is not some trick of the geometry that I chose. This is a general result. You can do it in other geometries. It's not so straightforward. This is a general result. Take this to the bank. The force, the magnetic force, acting on a closed loop of current is identically 0. Now be careful. The torque is not 0. We saw that a while ago. But the force is 0. Therefore, if you encase a loop of current inside a magnetic field and let it go, it will never translate. It will only rotate. Translation is not possible because the force due to the magnetic force due to an external field on a closed loop of current is identically 0. You can use this result just like we use some of the electric flux results to make really complicated problems really difficult. We take the same field, right? And I'm going to do this. Here's my current. I'm going to put this wire in this field. About there. I'm going to put this wire in this field and say, what's the force on that wire? And if you're going to do it, like we've been doing it, you're going to have to, you're going to find the current direction, which changes, and you're going to form an ILB sine theta for this guy, and an ILB sine theta for this guy, and an ILB sine theta for this guy, and you're going to add them all up, right? And then you're going to have vector cancellation that comes in because those ILBs are vectors. This is a force after all. And you're going to have to add them all up and figure out what cancels. Or you can do this. Can you calculate the magnetic force on this one? If you know what I is and you know what L is. Isn't that easy? Yes, no? What would it be? What is the force on this section? Yeah, force on this section is just I, L, B. Now, does that section of the wire actually exist? No. But if it did, couldn't you just calculate the force very straightforwardly like ILB? Right? What that means, what is the total force on this other wire? The one that actually exists? Minus ILB. You see what we did there? We exploited this fact that if I close this off, the force has to equal 0. So whatever this god-awful current is over here, this force I should say, it's got to be the opposite of whatever it is over here. This is the same thing we did with the flux, right? Where in your homework you had to, or I don't remember if I said this or not, you had to calculate the flux through this dome. And this is terrible, but then you figured out that it's got to be the same as the flux through this. Because the flux through any closed surface is 0. Same thing here. The force on any closed loop of current is 0. So if you have this crazy wire, you can do the addition of all of those, the vector addition. Or you can imagine that you close it, figure out whatever the force is here, and whatever the total force on the other has to be the opposite of that. Does that make some sense? Alright, so that's a very important result. The force on any closed loop of current in a magnetic field is identically 0. The torque is not. The potential energy is not. But the total force is 0. From that we get that a magnetic force will never make a closed loop of current translate. Okay? Alright. That will finish up chapter 11. We've already done most of chapter 12 here, so that's cool. Any questions on anything we've done so far? I realize I'm kind of hitting around in some different spots. They're related in my mind, but whether or not they're related in your mind. questions, I give you that.